quickly recap which we discussed in the last class. In the last class, we discussed about the derivation of Navier-Stokes equation, which is the basically set of continuity equation and linear momentum equation. So we derived these relation in the last class for the inviscid flow in which there is only normal stress, which is pressure. In that case, so in non-viscous fluid, there is no shear stress. So it means that we have got only normal stress, which is pressure in that case. And we know from our hydrostatic knowledge of chapter number 2 that pressure is a compressive force. So that's why we take minus sign with, we use minus sign for that. So after that, we discuss about the viscous flow relation in which there is an additional term of involving viscosity. We can see that stress is directly related with the normal velocity gradient. And similarly, we also discussed in the last class that shear stress components are the tangential velocity components. So all these normal velocity components and tangential velocity components were discussed in the beginning when we discussed about fluid element deformation. So in that we discussed in detail. So after we put these relation in the governing equation, which are shown on this slide, so we can get these relations. So these are the three linear momentum equation in x, y, and z direction, which govern the incompressible flows. So they are non-linear second-order partial differential equations, and the exact solution of such equations is not found yet for the complete equation, but for certain cases we can kind of simplify the equation so that it becomes ordinary differential equation, and then we can do the solution accordingly. So the situation in which we can obtain the exact solution for the velocity, those are like steady laminar flow between fixed parallel plates, and we called it Poisson flow. And then we have got steady laminar flow between fixed parallel plates in which one plate is stationary, which is the bottom plate, and one plate is moving. So that is called coed flow. And then similar kind of relations or solutions can be found for some flow through pipe, like flow through pipes or flow through annulus. So which is the space between two concentric pipes. So I hope that rest of the class has joined it. So now we focus on getting the solution for the Poisson flow. So if I kind of uh, zoom in it a little bit, one thing which I want to mention in this figure, that in this figure, which is the figure on the top, or maybe I can make it a little bit more. So if we see here that we have got the coordinate system, they are defined as the center of the plate rather than the lower plate. The reason for that is that after doing the solution, we will find out that the flow through this is symmetric along the center line. So that's why x coordinate or y coordinate is starting at the center, and x is similarly starting from here, and then z is outward. So let me go back to the original. So now we are going to discuss its solution, which is the Poisson solution, in which the both of the plates are infinite in x direction and z direction, which is out of the board, and then it means that there is only velocity in x direction, and then v and w velocity components, they are zero. And secondly, we have got the boundary conditions, like at y is equal to minus h, u is equal to 0, and at y is equal to plus h, we have got u is equal to 0. We need that when we need to solve ordinary differential equation, which would come in maybe in 5 minutes time. So then again here the assumptions are shown. Plates are infinite in x and parallel horizontal plates, so it means that there is only u component. The flow is steady and laminar, so it means streamline flow. Then the third assumption is fluid flows in the x direction only. It means that there is only u velocity component, v and w are zero. And the most important assumption there is the flow is fully developed in x direction. So fully developed means that if we travel along a streamline, then the velocity does not change in x. So it means that partial u by partial x, that is equal to 0. So that can also be obtained from the continuity equation if we talk about steady incompressible flow, because we know that for the steady incompressible flow we have got the relation partial u by partial x plus partial v by partial y plus partial w by partial v equal to 0. So in this case, we know that because for the steady laminar incompressible flow through between two parallel plates, we know that V and W components are 0. So it means that we can say that this is equal to 0, and partial W by partial Z is also equal to 0. So we can say that partial U by partial X is 0. So it means that the flow is fully developed. It means that the velocity is not changing in x along a streamline. So that is important to note. And then the fifth assumption is incompressible flow. Now, if we apply these assumptions to the governing equations, which are the Navier-Stokes equations, so I have done it here for your convenience. So if you see that there is a number written with each constellation, so that number represents the assumption we are using for the simplification. So partial u by partial t is equal to 0, because if we look at point number 2, the flow is steady, so there is no time dependence. Then partial u by partial x is equal to 0. Why? Because it is fully developed. Then, and the third assumption, the third term on the left hand side, v velocity is 0. So we have taken the third assumption, and then w velocity again. And then on the right hand side, we have, because it is infinite and parallel plate, so it means that gravitational constant in x is also equal to 0. And then because partial u by partial x is equal to 0, so if we take the gradient again for the 0, we all know that it would be partial square u by partial x square. So that would also be equal to 0. And then because the flow is only in the x direction, so partial u by partial z, that is also, it means that in the out of the board direction there is no velocity change if we move. So it has got the same velocity, so that's why partial u by partial z or partial square u by partial z square, that is equal to 0. So in the first equation, if we look that there is only two terms, one is minus partial p by partial x, and the second term is mu into partial square u upon partial y square. In second equation, which is the v momentum equation, all the terms on the left hand side, they are equal to 0, because the v velocity is equal to 0 and v velocity is coming in each term. And on the right hand side, then again the viscous term, that is also all the terms are 0, because v velocity is 0. And similarly, we can say the same thing for the w velocity, because w velocity and v velocity, they are 0. So if we write the simplified equation now for the x coordinate, for the x direction, it is shown. Uh, it is shown here that we have got the simplified form of the Navier-Stokes equation for the steady laminar flow between fixed parallel plates. That becomes x momentum equation is equal to minus delta p upon delta x plus mu into partial k u upon partial y square. And that is, here we have got minus rho g. Why is that? Because we have got gravitational constant, which is g. So it is minus because it is in the negative y direction, so that's why we have taken it minus. So if we want to get the value of velocity u with respect to y, we need to solve this equation, which is written on the right hand side. So let me write this equation again on the whiteboard. So d square u upon dy square is equal to 1 upon mu partial p by partial x. So in this case, if I write here, first of all, let's see. So here we have got d square u upon dy square is equal to is equal to 1 upon mu dp upon dx. It should be partial p by partial x, but we can easily write it by dp by dx. But let's uh, for the consistency sake, we can write it partial p by partial x for the time being. So it is the same equation. Now, if we want to get the value of u from here, what we need to do? Yes. Any question? What we need to do if we want to find the value of u from this equation? I think you know that once we have got differential, we need to integrate it. Yes. Well, anything you want to add? Okay. So if we take differential for the first time, we can write du upon dy is equal to 1 upon mu partial p by partial x into y plus c1. C1, sorry. C1, why we are writing C1? Because we have taken indefinite integral. So if we take, and now if we want to find the value of u, which is function of y, it would be equal to 1 upon 2 mu partial p by partial x y square plus c1 y plus c2. So now we have taken differential for the second time. So there is another constant which is C2 here, which comes due to the second indefinite integration. Now, if we want to find the value of C1 and C2, we need to apply the boundary condition. So the boundary conditions are such that it is the center. So at center we have got y is equal to 0. At here we have got minus h. Here we have got plus h. So at y is equal to minus h, we have got u is equal to 0. So it means that if we put it here, so 0 would be equal to 1.2 mu partial p by partial y into h square minus c1h plus c2. Second boundary condition is when at y is equal to plus h, u is equal to 0. So we can again write it 0 is equal to 1 upon 2 mu partial p by partial y h square plus c1 h plus c. So from here, if we uh, try to subtract these two equations. So we can see that this, and this. So this would be equal to 0. Here we would have minus 2c1h, and here it would be 0 and it is equal to 0. So it means that we have got 2c1h is equal to 0, right? So h is a finite value. It cannot be 0. 2 is not equal to 0. So it means that c1 is equal to 0 because h is a finite length. So c1 is equal to 0. And now if we want to calculate C2, so we can easily, because C1 is equal to 0, so C2 would be equal to minus 1 upon 2 mu partial P by partial Y H square. So this is the value of C2. So if we put it in the governing equation, which was this U of Y of this, so if we put this value here, so we can easily show that U of Y is equal to 1 upon 2 mu partial P by partial Y into it would be Y square minus H. So this is our velocity profile, and we can easily see that it depends on the second power of y. So it means that this is a quadratic equation, right? So we know that what is linear equation and what is quadratic equation. So if I so this was the general solution. So in order to get the specific solution, we need to apply the boundary condition. So if we apply the boundary condition, we can write it like this. So I hope that it is clear to you. And we have got u is equal to 1 upon 2 mu partial p by partial x y square minus h square. So now here we have got the value of u. So this pressure gradient, that is usually a negative thing. Because why it is negative? Because we all know that fluid flow happens from high pressure to low pressure. So that's why we put a pump when we need to flow some water from one place to another, like from your under storage tank to overhead tank in your home. So that's why we create high pressure at the pump side, and because there is a low pressure at the other side, so the fluid flows. So usually partial P by partial X is a negative value, and because it is a quadratic equation, so the velocity would increase, would be zero at the wall surface, which is due to no slip condition, and it would have maximum value center of the at the center between these two parallel plates, and then it would again reduce to this. Okay, now one thing that we need to determine, that is the volume flow rate. So in order to calculate the volume flow rate, what we need to do, because if you remember from your thermodynamics knowledge, because we know that Q is equal to AV, and V is their mean velocity. But in this case, if we see that that velocity is not a mean velocity, but that is changing with the y location. So what we need to do, that we need to integrate it from this point to this point. So if we do that integration here, we can write u into, it should be minus h to h, which is the distance between the two plates, into dy, which is a height here shown, and then the third z direction, because we need to have area there. So the third direction would be z, which is out of the board. So we take it 1. So dy into 1, that is the, for the unit width, if we want to calculate, so u into dy. Now how to calculate u into dy? We need to put this relation here. So and then integrate. So we know that 1 upon 2 mu is constant, and then partial p by partial, it should be I think it should be x not y in the relation. Partial p by partial x. So it would be partial p by partial x. They are constant values, so they would be out of integration. The things which can be integrated, so they would be something y square h square into dy. So if we integrate it from h to h, now I am taking only this thing. I am talking about this thing. So if I integrate it here, it would be y cube by 3 minus h to h and minus h square by minus h to h. So if we do that, it would be h cube by 3 plus h cube by 3. Why plus? Because minus into minus h cube by 3, so I wrote it plus h cube by 3, and then the second term would be here h cube plus h cube, right? So if I go a little bit down here, I can see that it would be 2h cube by 3 minus 2h cube. So if I do that, so this becomes equal to, if we kind of uh, we can easily see that it is equal to minus 4h cube by 3. So now we need to put it here. So uh, if we put this, so q would be equal to 1 upon 2 mu, so into 4 by 3, 4 by 3 h cube, and it should be minus here, and then here delta p by delta. So if I simplify it, I can write minus 2 by 3 mu h cube partial p by partial n. Right. So this is the relation which is derived here, minus 2 by 3 h cube divided by mu into partial p by partial x. But there is one thing very confusing, that there is a minus sign. So it means that the flow would be in the negative x direction, which is not possible because u is in the positive x direction. The only thing which needs to be considered here, that is partial p by partial x is a negative value, because the pressure should drop in order to flow in the x direction. The pressure should drop in the x direction. So if we do that, then we can write that if I say that we have got a pipe which is of length L, and we have got total pressure drop here, that is delta P, between this point 1 and 2. So we can write a pressure gradient like this: partial by partial x is equal to minus delta P by S. So that is the pressure which is final value to initial value. So that would be minus delta P by L, because that is, it is showing us that pressure is being dropped. So if we put that value here, we can, in the Q relation, then this minus would be eliminated, and we can write Q is equal to 2 by 3 h cube by mu delta P by. So this is our Q value in terms of pressure drop, not pressure gradient, but pressure. So this is the relation which can be written in terms of delta P. Now that is, I have explained that what is delta P. That is the pressure drop between 2 points. So the volumetric flow rate can be written 2 by 3 h cube mu into delta P divided by 10. So the same relation is written here. Okay, now one thing we need to know, that what is the mean velocity. So mean velocity, if you remember that, we can also write q is equal to AV. So here V is the mean velocity. So V would be equal to Q upon A. Now what is area here? Area here is this height, which is 2h into 1, which is the unit width. So it means that we can say that 2 by 3 h cube on mu delta P L divided by area is 2H into 1. So here 2 would be cancelled with this 2 and H would be cancelled with this H cube, it would be H squared. So V is equal to H square delta P divided by 3 mu L. So this is the relation for the mean velocity. Mean velocity mean I hope that you know the value, you know the definition of mean. It is defined as the velocity as a uniform velocity which would produce the same mass flow rate as the actual profile is doing here. So usually if we draw it, uh, so if actual profile is something like, let me go back here. If the actual profile is if the actual profile is something like this, if this is the cross section where we are looking at, if the actual profile, that's one, uh, if this is the actual profile, so the mean profile, mean velocity would be something like this, because that is a uniform value. At some portion it would be less than the actual velocity, and at some portion it would be greater than that, because only then it would have the same mass flow rate, right? So mean velocity would be less than the maximum velocity, but it would be greater than the minimum velocity, which is the zero velocity at the uh, 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 plate. So now if we want to calculate the maximum velocity, so it means that we need to have this relation with us, which is u of y is equal to 1 upon 2 mu partial p by partial x. We can write here minus delta p by l and y square minus l. So let me rewrite that u of y is equal to 1 upon 2 mu, and then it was minus delta p by n into y square minus h square. Right. So if we look at the figure here, where would be maximum velocity? It is at the center, which is the place when y is equal to 0 at this place. So it means that when we put y is equal to 0, we would have u maximum. So I can write that u maximum is equal to minus delta p divided by 2 mu l into minus h. So that would be equal to delta p h square divided by 2 mu l. So if you see here we have got h, the numerator is the same here. The denominator is a little bit different. So if we want to incorporate this mean velocity in this relation, so we need to divide with 3 and multiply it with 3. So if we do that, we can say that it would be 3 by 2 into h square delta p divided by 3 mu l. We haven't done anything wrong. We have multiplied it with 3 and divided it by 3. So now you can see that this is the mean velocity which is here. So we can write that u max is equal to 3 by 2 v mean. We write it v mean velocity. So maximum velocity is 1.5 times of the mean velocity for the steady laminar pipe flow. So the steady laminar flow through between two parallel plates. Right. So now we have done this. Any query up till now? If you have got any query, you can ask. Otherwise, we can continue with the some of the numerical related with the this flow through between two parallel plates, and then the thing. is to be discussed today. So it seems that everything is clear, so which is very good. So now we do a couple of numerical, or you can say that derivation. So first of all, we have got a situation in which oil whose which viscosity is given 0.4 Newton second per meter square flows between two fixed parallel infinite plates with a spacing of 5 mm. Now the total distance is 5 mm. So because if you remember that okay, maybe okay. If we go back, that the spacing here when we started it was 2h. So 2h is equal to 5 mm in this case in the numerical, that 2h is equal to 5 mm, and the flow is laminar and steady with a pressure gradient of minus 900 Newton per meter square. Determine the volume flow rate per unit width and the shear stress on the upper plane. Now we need to calculate these two things. The one is the volumetric flow rate, and the other is the shear stress. So let's do this problem on the whiteboard. So first of all, we have been given that uh, that uh, that the gap between those two are 5 mm. So 2h is equal to 5 mm. So we can say that h is equal to 2.5 into 10 to power minus 3 meters. Second thing is partial p by partial x, that is given 3 minus 900 Pascal, which is Newton per meter. Right. So we need to calculate Q value. So Q value can be calculated by the relation we just derived, which was equal to 2h cube delta P divided by 3 mu n. And mu value is given equal to zero point 0.4 Newton second per Newton second per meter. So Newton second per meter square. So now delta P by L would be equal to minus delta partial P by partial X. So that would be equal to 900. So that is quite simple. Now we can put the values 2 into 2.5 into 10 to the power minus 3 cube into 900 and 900 delta P by L, which is the value, and then 3 into mu value is zero point 0.4. So if we do that, we get the value of Q, which is equal to 2.34 into 10 to power minus 5 meter meter cube per second. So because it is volumetric phenomena, so I have written per meter cube. But if it is per unit weights, we can equally write it meter square per second. So now the second thing is the shear stress, which is this this upper plate is experiencing. So first of all, we would determine the shear stress which is being applied on the, because let me. So if this is a pipe surface, so this is kind of a zoomed in view. So if this is a fluid element which is here, so here we are going to calculate the shear stress on this element, and then the equal and opposite shear stress would be applied by this plate. So we would see that what is that. First of all, we are going to find the stress value on this top surface of the fluid element. So if we want to calculate that, we know that tau xy is equal to mu into partial u by partial y plus partial v by partial x. So now we know that how to calculate partial u by partial y in this case, because we know the formula that we calculate u here, u by is equal to 1 upon 2 mu minus delta p by L into y square minus s square. So if we take the differential of this equation, there would be 2y here, right? So that would be equal to 1 upon 2 mu into 2. So 2 would be cancelled with 2, and it can be written minus delta p upon mu L into y. So let me write that there. So we have got partial u by partial y would be equal to minus delta p upon 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 2. 2 would be cancelled. Okay, so mu L into y into y, which is due to the differentiation with respect to y. So because now we want to calculate it at the upper surface of y is equal to h there, so we can replace it with h, right? So we have replaced it with h. Why? Because we are going to determine it at y is equal to plus h. So and now we also know that partial v by partial x is equal to 0. Why is that? Because v velocity is 0 for this case. So let's put this value here. So if we put the values for tau xy, that is mu into minus delta p on mu L into L. Now mu would be cancelled with this, and this is minus delta p h divided by h. Now this is the shear stress which is being applied on this fluid element by the pipe. Now equal and opposite shear stress, because if you can easily see that if this element is moving in this direction, it would kind of get experience some resistance in the negative x direction due to this flat plate. So on this surface, the tau yx would be negative, and equal force would be applied by this element on the pipe surface. So this is the tau xy. This is the shear stress applied on the fluid element on the element. And if I want to find the value of shear stress applied on the pipe surface, that would be equal and opposite to this. So that would be equal to delta p h by L. Right? Because I have just explained that if this fluid is experiencing a shear stress in the negative x direction, so this pipe surface would also experience a shear stress in the positive x direction, which is the basically the comes from Newton's third law of motion, that every action has equal. So the equal and opposite force would be acting on the pipe surface. Right. So this was, now we can calculate its value. So delta P by L, that is 900, and H value is 2.5 into 10 to the power minus 3, and that would give us some value. So it would be, I think, 2.25 acting in the positive direction if we talk about the on the pipe surface. Right. So this was first numerical. Any query in that? Please let me know. There is no query, then that's good. So we continue with the second numerical problem. Now we have got two parallel plates, but the difference here that the direction of flow is in the positive y direction. It is not in the x direction as we did the case for the flat Poisson flow. So now it means that we would also have the contribution of that gravitational force in because now it is partial y. So we need to determine the expression for the pressure gradient in the direction of flow, and then we need to write it in terms of mean velocity. So the flow is laminar, steady, and uniform. So we know that because this is y-direction equation, so it means that we need to consider the y-direction momentum equation. So let's we can write that equation here. So that was, if you remember, that was rho into partial v by partial t plus v into partial u by partial x plus partial v by partial y plus I think it is a little bit, it should be the way down. It should be u into partial v by partial x plus and then it would be w into partial v by partial z is equal to minus partial p by partial y minus rho g plus 1 upon mu partial square v upon partial x square plus partial square v upon partial y square plus partial square partial v upon partial z square. Right. So uh, because let me draw that here for simplicity of the discussion. So if I draw those plates here, now we are going to start x-axis from the center because we know that that is kind of, because we know that the if we kind of see the velocity profile, it would be something like this, right? Because it is going upward. It is like the flow of water going from vertically from your understory tank to the overhead tank. So here there would be some pump which is installed in your homes, and then water goes up from there. Okay, so we are going to start x-axis from here. So x is equal to 0 from here, and we also know that partial v by partial x would be equal to 0 because the flow is fully developed. So it means that the the velocity along a streamline would be equal to 0. First of all, because the flow is steady, so we can say that partial v by partial t is equal to 0. Then we can also say that u is equal to 0 because that is vertical velocity. And then second thing, partial v by partial y would be equal to 0. Why is that? Because the flow is fully developed in the y direction. So it means that if the flow is going upward, so if it follows a streamline, the particle would have the same velocity. Similarly, because there is no pressure gradient in the z direction, so u and d velocity, u and w velocities are zero. So partial w by partial z, or we can also say that w velocity is zero. So then partial p by partial y, that would be a non-zero value. Rho g, that is due to the weight, the gravitational constant that is there. Now partial square v upon partial x square, that would be non-zero because why is that? Because v velocity is changing in x. But partial square v by partial y square, that would be zero because the first derivative was zero, and then again partial square v by partial z square is zero because there is no change in velocity in the out of the board. So now we have been left with the equation minus partial p by partial y minus rho g is equal to, we can say that it is equal plus 1 plus it shouldn't be 1 upon mu, it should be mu. It should be mu, okay, plus mu into partial square v upon partial x, right? So is equal to 0. So now we can write that partial square v upon partial x square is equal to 1 upon mu into partial p by partial y plus rho g, right? So now because these are constant values, so let's take this for the simplicity of the writing thing. I take it equal to uh, capital P. So capital P with a small line here. So that is representing this constant value because that pressure gradient is also a constant value. These constant rho is constant because that is incompressible fluid. So we can write partial or we can write d square v upon dx square because v is only dependent upon x, that is equal to p upon mu, right? So now if we want to calculate its v velocity from here, that is very simple. First of all, take first derivative. So if we do that, so v dv by dy would be equal to p upon mu into y plus p1. Now, because we know that at the center here, we would have a maximum value. So gradient would be 0 there. At x is, it shouldn't be y here, it should be x. Because we are taking integral in x direction. So it would be x here. So we know that dv by dx at this point would be equal to 0 because there is a maximum point. So if we say that at x is equal to 0, which is this center location, dv by dx is equal to 0, it gives us c1 is equal to 0. And then if we want to calculate v from here, we take the second differential. So that would be equal to v of x is equal to p by mu into x squared by 2 plus C2 because C1 is also already 0. So now if we want to calculate C2, only we need to do is that put at x is equal to at x is equal to h. H is the distance from the center line. If you look in this figure, so it means to say that if I show it here, this is also h. So at So I can write that v is equal to 0 at x is equal to plus h or x is equal to minus h for that matter. So from here I can see that C2 is equal to P, which is this thing, the combination of these two terms, that is a constant value P upon 2 mu with the minus sign into h. Right. So if we say that v is equal to 0 at x is equal to minus h, which is this location, then we would have the same relation. There would be no difference. So if we write the now if we put that C2 value here, we can write v of x is equal to p upon 2 mu x square minus h. Right. So this is our velocity profile for this flow. That ball normal or the y direction velocity would be equal to this. Now, if we want to calculate q value, that is again we know that for the q calculation we need to have v into p of y into d of x into 1. d of x. Why we are it should be u, of x, not v. So v is only function of x. Dx into 1 minus h to plus h. So if we do that, p upon 2 mu would be out of integration minus h to h x square minus h square into dA. So either if you remember that similar kind of integration we did for the Poisson flow, in which there was y square minus h square into dy was there. So we know the answer would be equal to q would be equal to it would be minus uh, minus, if I write the final relation, it would be equal to minus 2 by 3 h cube upon mu into p, right? So now again there is a minus here. So we know, because we know that partial p by partial y is a negative value, so it would be kind of catered for in that. So this is the relation in terms of uh, uh, that if I put that value here, it would be right. So we know that this value is again negative. G is also a negative value, so it would be in fact uh, having a positive value in the y direction, which is upward direction. So this is the value, and then we can easily write it in terms of mean velocity as well, because we know that mean can be calculated from that was v would be equal to q upon 2h, and then from there we can write it in that term. So I hope that this these two numerical problems are also quite understandable. If there is any query, you can let me know now. Otherwise, we can have a break for 10 minutes before we come back and discuss our next topic. Any query? Any? Okay, it seems we are good at that, so we would meet in 10 minutes then. Thank you. Okay, ji, welcome back. I'm going to share my screen. So, so can anyone confirm that you can see the screen as well? Anyone?
Yes, sir.
Okay, thank you. So, before going on the break, we discussed about the flow through. Just so let me. So we discussed the derivation for the velocity profile, then volume flow rate for the steady laminar flow between fixed parallel plates when the both plates were stationary. It means that the both plates were kind of having zero velocity. But there is another type of flow which is called coed flow, in which in this we have got the lower plate has got the zero velocity and the upper plate has got some finite value. So usually this type of flow that occurs in the ball bearing, because if we take the ball bearing and we know that even that is a circular object, so we can flat it out. So in that the one of the inner surface that is stationary and the outer surface is moving with the rotor shaft. So so that is kind of flow which happens in ball bearing or general bearing. So we are going to do the same derivation for that. So because we know that the general solution was equal to u is equal to 1 upon 2 mu partial p by partial x y square plus c1 y plus c2. So the general solution would be the same for Poiseuille flow as well as for the coed flow. The only difference uh, here would be the application of the boundary condition. Now if I show you that now, because we know that the upper plate is moving with a uniform value u, so it means that now we have changed the coordinate system. For the Poiseuille flow, it was starting from the center, but now it is starting from the lower plate. From the lower plate at y is equal to 0, we have got zero velocity at y is equal to b. B is the distance between upper and lower plate. If you can see it, maybe it is not very visible, but let me make it a little bit more visible. So if you look here, we have got at y is equal to 0, we have got fixed plate at y is equal to 0 because the coordinate system is starting from the lower plate. And at y is equal to b, we have got uniform value for the plate which is moving with a velocity capital U. So now let's see that how its specific solution would differ from the solution which we obtained for the Poiseuille flow. The general solution would be the same, which is written here: u is equal to 1 upon 2 mu partial p by partial x y square plus c1 y plus c2. So let's go on that slide. So bottom plate is fixed while surface is upper plate moves with a constant velocity u, which is for the coed flow. So the same assumption and simplified form of the Navier-Stokes equations as for the Poiseuille flow. So u is equal to 1 upon 2 mu partial p by partial x into y square plus c1 y plus c2. Now, if I write this on the whiteboard again. U is equal to u of y is equal to 1 upon 2 mu into 1 upon 2 mu into partial by partial x y squared plus t1y plus t. Right. So this is our general profile. Now we need to apply the boundary conditions to get the value of C1 and C2. So first of all, let me draw the schematic here. Here, this is y is equal to 0, so u is equal to 0. This is the fixed plate. Now this distance is b, and here the u is capital U at y is equal to b. So at y, so first of all, we put at y is equal to 0, u is equal to 0. So if we put it in this equation number 1, we can see that this term is 0 because y is being multiplied. This term is also 0 because y scale is here, and the u of y, that is 0. So that is, we can write C2 is equal to 0. Right. So C2 is equal to 0. Now the next boundary condition, when y is equal to b, u is equal to capital U. So we can write capital U here, 1 upon 2 mu partial by partial x x into b square plus t1 b. Now from here, if we want to calculate t1, that would be equal to u upon b minus 1 upon 2 mu partial p by partial x into b. Right. So now we need to put this here at this point. So this whole thing is going here. So if we put this value here, we can say that u of y is equal to u divided by b into y, because y is being multiplied here, and then the next term we can write like this: 1 upon 2 mu partial p by partial x into y square minus by. So now we can see that the velocity profile is not kind of quadratic, because there is also a linear term here, So it means that now it is not quadratic. So we can also write it in a non-dimensional form. So in non-dimensional form, we need to do a little bit of mathematical manipulation of the term, but we can write it like non-dimensional means that each term has 0 dimensions. So if we divide the whole equation with u, so u divided by capital U, so here it would be y upon b. So it's u upon u, that is non-dimensional, y upon b, that is also non-dimensional, and then here we can write it equal to, or we can minus, now we want to write it by minus y square. So if we do that manipulation, we can write it, and that you can do it on your own time if you want to know that how we get here, because once we divide it by u, so u would also come here, and partial p by partial x into y upon h 1 minus y upon b. So now if we look here, that almost all the terms are non-dimensional. So it means that we have written this equation in non-dimensional form. So now if I I'll show you the slides here. So when we put that, we have just derived this on the whiteboard that u becomes equal u of y is equal to u y upon b plus 1 upon 2 mu partial p by partial x y square minus dy, and then the velocity profile becomes equal to, in the non-dimensional form, as I mentioned, that can be derived with the maybe 1-2 minutes job. You can do it as it is quite easy. So this parameter, this b squared to mu u into partial p by partial x, it determines that what is the velocity profile here. The simplest case is that this parameter is zero when there is no pressure gradient within that plate. It means that the flow is only happening due to the motion of this plate. The upper plate, there is no pressure drop in the between these two plates. The flow is only happening due to that flow of this plate. So the upper movement of that plate. So that is the simplest case. So this parameter, as I told you, that this defines that what would be the profile. Now, if the p value is positive, you can see that there is a pressure drop. So it means that in Poisson flow it was something like that. That from here it was something like this. But because now there is a motion of the upper plate, so you can see that depending upon the p value, the initial and final value, they are same, but how they reach uh, from lower plate to the upper plate, the velocity profile, that is dependent upon this parameter p, which has been defined here, right? So this is the place where we have defined that p parameter. So this is a non-dimensional pressure gradient. So we call it non-dimensional pressure gradient. So if that value is negative, it means that here p, if it is -3, what does it mean? That if it is minus here, then here it would be positive, and then it would be kind of flow where we have got pressure increase in this direction. But it p value is positive here, like 3, so it means that there is a pressure drop. When there is a pressure drop, the velocity in the center would be higher. And here, when p is equal to -3, it is or -2. For that sake, you can see very interesting behavior of the velocity. That the velocity becomes negative value in the middle, and then it goes towards the positive value of the this plate, which is so that is due to that plate. But in the middle, due to that pressure increase, we have got kind of reverse flow, right? So the simplest form of the coed flow is one with the zero pressure gradient. So the line, which is a straight line here, which is this straight line which is showing p parameter is equal to 0. If you, so that is the simplest case, and in that the velocity profile is just because if you see this equation, if the second term is equal to 0, then u is equal to y upon b into capital U. So this is the velocity profile in this case, which would be linear. So this was these were the two cases which we needed to discuss in chapter number 6. Now this was just about the derivation of the Navier-Stokes equation for the compressible viscous flow, right? So now, as you can see, that we can only get the uh, exact solution for very simplified cases. We cannot get the solution when we have got unsteady flow, or we have got multi-dimensional flow where u is also function of x and y and z, which is the case when the flow goes through like certain turbo machinery applications, or flow over aeroplane, or flow over vehicle. In that case, in those cases, we cannot get these velocity profile which are being obtained by converting the uh, converting the governing equation into ordinary differential equation. Where the mouse cursor is, you can easily see that this is an ordinary differential equation, and we can get the exact solution by the integration. But unfortunately, this is not the case when we happen to analyze some interesting engineering applications like flow through turbo machine, flow over ships or aeroplanes. Then it means that we need to either conduct numerical, conduct experiments to see that, or we can either do the numerical solution, which are by using software. So chapter number 7, which you out to cover in chapter in fluid mechanics 1, as you told me, as I remember correctly, that you haven't covered in FM1. Is that the case? Anyone? Have you covered chapter number 7 in your FM1, which is this chapter called
No,
dimensional
sir.
analysis? Uh, because it was
No,
included.
sir.
Are you pretty sure about that? Ashir
Yes,
or
sir.
Hassan Mustafa? Is
Yes,
this
sir,
the
sure.
case? Because whenever I teach this course, because I have taught this course for maybe, I am teaching this course maybe fifth, sixth time at the moment. So I usually cover first 5 chapters in FM1 and then the chapter 7, because that is needed, because once you do the experiments in FM2, you need to know that what kind of experiments you are doing and what are the different parameters you are choosing for the experiment. So that is very important before you conduct the experiment. But maybe due to the DL mode, Salomare couldn't cover that chapter. So I think I would quickly go through this chapter just to make sure that the experiments you are doing, that what is the purpose and how, if you are conducting it in the water tunnel or wind tunnel, then how to convert those results for the practical application you are conducting that experiment for. Okay, first of all, without going into details, uh, how to conduct an experiment on a, let's suppose that we want to analyze a Boeing 777, that wing of that. So how to conduct that experiment in a laboratory? Because we know that that wing is very large thing. So it means that the wind tunnel which is required for the conduct of experiments, so that we can find lift and drag on the on that aerofoil. So that would be very huge and it would be very expensive to build, and maybe it is not viable for that. So what we do, that we make models of the actual thing, so we can scale it down to a manageable level, so that we can put that into some wind tunnel, right? And then we can conduct the experiment. Now, the second thing, okay, scale down or scale up. Scale up, if we are talking about nano objects, then we need to scale up so that we can kind of apply that experiment in wind tunnel, because on nano scale it is very difficult to visualize things. So we can scale up by using some scale up models, or we can scale down if we are talking about very huge structure. So second thing, now what is the case that if we have got an uh, uh, thing on which we need to, let's suppose that we need to calculate u value, and it is a function of x, y, z, then pressure gradient, then viscosity, then rho, then whatever values. So it means that if we have got, first of all, we write the functional form. We call it functional form. Functional form means that the dependent variable for which we want to conduct the experiment, dependent variable that is written on the left hand side, and all the independent variables, uh, they are written on the, they are independent variables. So they are written on the right hand side. So it means that velocity is a function of x, y, z coordinates, that pressure gradient, viscosity, and density, and the surface roughness, and what not. So it means that we have got like 10 parameters there. So it means that if we want to study the variation of u with respect to each variable, each independent variable, then we need to get one variable constant, one variable, we need to change it, and then we need to keep all other constants. So it means that we need to keep other six, maybe here we have got 1, 2, 3, 4, 5, 6. So it means that first of all I would change x and see that how u is changing, and then other five variables are constant, and then y would be changed, and then the remaining would be constant. So it means that that is very tedious process. So what we do instead, that we make dimensionless parameters. Dimensionless parameters like Reynolds number. Reynolds number is the is the most significant parameter for fluid mechanics. It tells us that whether the flow is laminar or turbulent depending upon its value, its definition. For the pi flow, it is rho Vd upon mu. So this is basically the what do you call it, the ratio of inertial forces to the viscous force. So in this case, we have got dimensionless parameters. So we kind of want to introduce dimensionless parameters here in the dependent variable side and independent variable side. So that process is called dimension, dimen, dimensional analysis, in which we kind of see that what variables are important for this flow, and then what is the dependent variable, what is independent variable, and then what is how to make it non-dimensional parameters. So advantage of doing non-dimensionalization is twofold. One is the number of variables for the experiments are reduced, and secondly, then we can compare the results of one of experiment conducted in one wind tunnel with the experiment which are conducted in another wind tunnel having the same Reynolds number. So we can compare the results. So for the comparison purposes, it is quite easy if we have got dimensional. If we are conducting the experiments in dimensionless quantity. So these things I have given you overview, but as we go through the slides, all these things would be clear to you. So let's go through a few slides. So as I mentioned in the beginning, that why we need experiments, because analytic solutions are not available for many practical engineering for situations. So the solution to many problems is achieved through the use of combination of theoretical analysis and experimental evaluation. So dimensional analysis is the chapter number 7, which is of your book. So that is the study of techniques used for planning. Planning means that how to identify what are the critical parameters, independent parameters which we need to consider in the experiment, and then how to execute that experiment, and then how to correlate the experimental data. And then similitude, it means that a measurement made on a system, which is actual system, can be used to describe the behavior of other similar systems, which are, as I mentioned about the downscaling of Boeing 77 wing, so that we can downscale it, and then we can conduct the experiment in the wind tunnel. So the system studied in lab, they are considered to be models, right? So the actual one is the prototype, and the model we use for the evaluation in the experiments in the lab, and then from these models, empirical correlations can be developed. Now, why we conduct experiments? Because we need to find the behavior that how the dependent variable is changing with the change in independent variable. So, because we have got like on if we conduct experiments, so if we are conducting experiments between two non-dimensional parameter like uh, u upon u, which is non-dimensional, then the second parameter is x upon b. So there would be wealth of data which is getting. So we need to kind of do the curve fitting, because once we do the curve fitting, we can see that what does this variation look like, whether that is exponential, that is what is the best fit for that data. So once we get whether that is quadratic, that is exponential or Gaussian or whatever distribution is there, so so that we can come up with some empirical correlation. So in the software like MATLAB, it is very easy to, if we have got XY data, we can easily do the curve fitting and get different kind of empirical correlation. So it is kind of, but getting that accurate data, that is a challenge. Getting that empirical correlation, that is just a job of 5 minutes, not more than that. In order to achieve this, it is necessary to establish a relationship between the lab model and the actual system. So that relationship, how to get that? That is modeling. That thing is called modeling. That how to, because when we take our actual system and reduce it, then we need to make sure that the flow situation which the actual system is experiencing in actual, that are replicated on that downscale model. So that is made sure by the modeling approach. So that is which we're going to learn in a week or so. So as for the example, as I was mentioning, that let's consider that we talk about turbulent flow, not laminar flow, which is streamline flow, but the turbulent flow. So for the turbulent flow through a circular pipe, so for the turbulent flow, there is no exact solution at all, because for the turbulent flow there are fluctuations. So the partial differential equation cannot be reduced to ordinary differential equation. So pressure drop per unit length is a critical parameter. So because we need to know that for how much horsepower we need to apply at the beginning, so we need to select the pump for that particular uh, flow through pipe. So that is the critical parameter. So analytic solution is not possible. So we need to first of all we need to list down the variables which are important for that experiment. Now this is very critical step, because if you miss some critical parameter which needed to be included, but you didn't include it, then it means that whatever dimensional analysis you would be performing, that would be not very accurate, because you have missed a critical parameter. And those the knowledge of critical parameters for a particular flow comes with experience or with your engineering knowledge about that particular application, right? So the selection of critical parameters on which the pressure gradient would depend, that is entirely upon the engineer which is conducting the experiment, right? So it means that doing only the numerical stuff, that is not important, but building the engineering knowledge and understanding, that is more important than doing all these numericals, because you need to be a good engineer. To do that, you need to have a comprehensive knowledge of the field, rather than only doing these numerical calculation like I do on the whiteboard, because that is the purpose of only demonstration. Because in actual engineering applications, you are not required to do these numericals. Please be aware of this fact. You are going to design something in actual field. So for that, either you would do experiments or you would be using some kind of software for the analysis. Not doing these very fundamental numericals. They are only just to demonstrate you that how things work for a simplistic cases. But you need to know these things before you can understand those complex things. Okay, so these are equally important, but actually you are going to do these things which are a little bit more comprehensive. So first of all, we write the functional form that pressure gradient is dependent upon these four parameters. Now the first way of doing is that we conduct, because we have got four dependent variables, so it means that we need to conduct four types of experiment. In one, we have got delta p as a function of velocity, diameter, then rho and mu, and then all other three are constant respectively. But it doesn't tell you much about the whole phenomena, because it tells you the individual dependence, but it doesn't tell you the combined effect. And sometimes it is very difficult to change to keep all other variables constant while keeping one changing. Like if you change mu, then it is very difficult to keep rho constant for the same fluid, right? So maybe it is not very practical to conduct this type of experiment that only change rho and keep mu constant, because mu would change with rho, right? So this is quite difficult. So instead, what we do, that we make make it non-dimensional. The functional form which was represented here, which is written here, we make it non-dimensional, like this formula which is written here. And you can readily see that rho Vg upon mu, that is the Reynolds number. Now delta P is also made non-dimensional with the multiplication with diameter and division with rho V square. Now it is very easy. We need to conduct only the experiment of this quantity, which is non-dimensional pressure gradient with respect to Reynolds number. So the problem of conducting experiment, it is greatly simplified. Now how to conduct these experiments. Now, you would be wondering that how they are non-dimensional. You can either use MLT system or FLT system, which you have discussed in chapter number 1, and we know all the dimensions that delta PL is FL minus LE, because it is delta PL means delta P divided by delta X. So FL minus 3 diameter is only length, and then rho we know that we can calculate it in FLT system, and mu as well, velocity, that is meter per second. So we can see that these two are non-dimensional. Now how to get these non-dimensional, how to get this thing. So for that there is certain procedures that we need to apply on the functional form in order to get the non-dimensional products, and we call it pi terms. Okay, maybe we would discuss that in the next class. So these are called dimensionless products, or we also call it pi terms, pi terms. So how to do it? There are certain theorems, Buckingham pi theorems, or method of repeating variables. So all these we are going to study in the Friday's class. So is there any? So I just told you about the importance of dimensional analysis, modeling, and simulation, and their importance for the conduct of experiment. So if there is any query, you can ask me now. Otherwise, I am going to take the attendance now. I am going to download the attendance. I have downloaded the attendance, and if there is any query, I would wait maybe 30 seconds. You can ask